we're going to graph r equals 2 minus 2 cosine theta. And so now normally what I would make everybody do is I would, if we were not like on the time constraint of COVID distance learning, blah, 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 I'd make us plot all of these points and it would be absolutely miserable. And instead of doing that, we're just going to take a general idea of what these graphs, where it is a plus or minus b sine theta, or a plus or minus b cosine theta. These graphs that follow these formats are called lemmasones. I think there's like a little squiggly something or another on the C. It's French. It means like snail or something like that. Something like that. Oh, look, Gina's back again. All right, so these are called lemmasone. And the first lemmasone that we're going to deal with is the lemmasone in which the ratio between A to B is equal to 1, right? Would you agree that the ratio between 2 to 2 is 1? Everybody agrees with that? Okay, cool, good. Ah, perfect, all right. This specific type of lemmasone where that ratio is 1 is called a cardioid. And I bet you know enough about like Latin roots and all that junk to be able to tell me what this should generally resemble.
A heart.
Wow, that was great. Great job. So yeah, this is going to sort of resemble a heart. Now, what's going to happen with this is it's going to lie, the majority of it is going to lie in the quadrants where cosine is negative. And we'll know that because it's 2 minus 2 cosine theta. So the biggest piece of this is going to lie where cosine is negative. Which quadrants is cosine negative in? And this is the part where you answer.
The left side.
The left side, quadrants 2 and 3, yes. Now, the cardioid, or this lemmasone, is going to extend out 2 plus 2 units into quadrants 3. I should have written 2, quadrants 2 and 3, right, in that direction. Now, the reason it's 2 plus 2 units is because the A and the B value are both 2. So this is going to have a point 4 units over. That's going to be the furthest point away from the pole that we have. Every cardioid will also have a point that is at the pole. And the cardioid will circle around like this and circle around like this. And it doesn't look perfectly like a heart, but it generally looks like a heart. It's got sort of the shape of a heart to it. It comes in at a cusp here at the pole, right? We're familiar with what a cusp is, hopefully from last year. So it should come in at a cusp there at the pole. And what I'm going to do is I'm also going to pull this up on Desmos just because I graphs all the time. You'll be able to get a better idea of what it looks like. This is what it looks like if you type it into Desmos. Right. So we'll see that we went 4 units. That's the 2 and the 2, 4 units to the left. It comes around and it has a cusp at the pole. It is symmetric across the polar axis. And we will note that anytime we have a lemmasone with cosine, so lemmasones with cosine are all symmetric across the polar axis, no matter what, all the time, 100% of the time. What do you think would have happened if we had had this lemmasone be 2 plus 2 cosine theta?
It would be the same thing, except it would be on the right side.
Yep, it would have the majority of it in the quadrants where cosine is positive. That'd be quadrants 1 and 4. All right, I'm going to put this on the polar grid just for fun here. Okay. Everybody good with that? Any issues there? That is one of 4 different types of limasones that we will deal with. And it is the limasone that is a cardioid that looks sort of like a heart. Cool. We're going to do another one of those real quick here. 1 plus cosine theta. So you should be able to, I hope, sketch a graph of 1 plus cosine theta, r equals 1 plus cosine theta. It should look like a cardioid. It's a limasome that is a cardioid because the ratio between the A value, which is 1, and the B value, which is also 1, is 1. It should extend into the quadrants where cosine is positive 2 units, and it should look about like that. Everybody good with that?
Great.
Okay. Do we need to look at it on Desmos? No. We could. Why not? Look. Oh, no, this one's green. Look at that. So much different than my graph. My graph was red. Any questions? Any issues with that? Everybody good? Cool. Actually, before we move on to that, what would happen? We're going to go back to Desmos. What do you think would happen if I turned this into sine instead of cosine?
It would go up instead of to the right.
That's right. It would have the larger portion of it in the quadrants where sine is positive. And if I had a negative sign there, it would be predominantly in the quadrants where sine is negative, quadrants 3 and 4. And if I made this 3 plus 3 sine theta, then it's just going to extend up 6 full units. But since the ratio is still 1 between them, we're still going to have that cusp at the pole. Everybody good there? Cool. All right. So let's move on to the next one. We've now got r equals 1 plus 2 sine theta. So this is still a limasone. This particular limasone, though, does not have a ratio between A and B that is equal to 1. What's the ratio between A and B?
1/2.
It should be 1/2, exactly. And so anytime we have a ratio between them that is between 0 and 1, so if A to B is, we'll say less than 1 but greater than 0, these limasones end up having an inner loop to them. Now, I'm going to try to sketch this on my own, but then we'll look at it on Desmos right afterwards because it'll look a lot better on Desmos. So there's going to be an outer loop and an inner loop to this. So the outer loop will extend out into the quadrants where sine is positive because this is plus sine, and it will extend out 1 plus 2 units, or A plus B. And it has an inner loop that will also extend into the quadrants where sine is positive, but it will go B minus A units, or 2 minus 1 units. Everybody good with that? So it's going to have, and I'm going to do my best to draw this, but it's not going to be real pretty. It's going to have an outer loop that goes out to 3. Then it's going to come in and have an inner loop that goes up to 1, and then it's going to come back around. And it's going to basically look like that, if you can imagine that I did that really nicely and artistically. So r equals 1 plus 2 sine theta. There it is. Okay. Isn't that great? Doesn't that look wonderful? Yes is the correct answer. What if I change this to 1 plus 3 sine theta? What would happen?
It would extend out 4 units and the inner loop would extend out 2 units.
Wonderful. If I made that 4 sine theta, then we'd go out 5 units and 3 units. If I made this 3 plus 4 sine theta, that ratio is still between 0 and 1. And so it will be 7 units out and just 1 unit for the inner loop. Okay. You could do this 2 plus 4 sine theta. What do you think would happen if I made it a minus sine theta? Should just flip down below the polar axis, right? What if I changed it into a 2 minus 4 cosine theta? Should be predominantly in the quadrants where cosine is negative. And if I made it a plus, it should be predominantly in the quadrants where cosine is positive. And we'll note that any time that, I'm going to go back to the sine one real quick. Any time that we have a lemniscus that has sine in it, it should be symmetric across the line theta equals pi over 2. So that's another important point that we're going to want to note. Any lemniscus with sine has symmetry across theta equals pi over 2. Everybody good so far?
Uh-huh.
Cool. All right. Now we've got r equals 3 minus 2 cosine theta. So this is still going to be a lemniscus. This time, what is my ratio between my A and my B?
3 halves.
3 halves. So A to B is 3 halves. And hold on 1 second, sorry. Oh, sorry about that. Helping my kid out with something here. Anytime we have a ratio for A to B that is greater than 1 but less than 2, this lemniscus has a, what we call, a very technical term here. Our lemniscus will have a dimple. It's a lemniscus with a dimple. And this dimple is really just, it's just a cusp, but it's a cusp that is not at the pole. Okay. So this one, 3 minus 2 cosine theta, should have the majority of it in the quadrants where cosine is negative, so quadrants 2 and 3. And it should extend out A plus B units, but it should also extend out in the opposite direction, A minus B units. So this one will have the furthest part out in the quadrants where cosine is negative 5 units. It should come around, oh, that was really horrible. It should come around and have, that's really horrible too. It should have this little, wow, that's really bad. Should have this little dimple here at 1. But it should still extend out 5 units here. So it should have this little cusp at 1. And because of my atrocious ability to draw, what was it, 3 minus 2 cosine theta? So you can see it sort of has this little dimple that pops in here. So out 5 units in 1 unit. If I made this, 4 minus 3 cosine theta, we'd see that it's still got that same thing going on, but it's still at 1 because a minus b is still 1, but out here it's gone out to 7. If I change it to a plus, same things apply, it just flips around. If I made it a sine, it's going to go up. If I made it a minus sign, it's going to go down. Everybody good with that? I'll assume that's a yes. All right, cool. Now we've got r equals 3 minus cosine theta. This time our ratio between a to b is equal to
3.
3. And this is still a lemniscus, but it's a lemniscus with a flattened side. And anytime the ratio of a to b is greater than or equal to 2, that's the kind of lemniscus that we will have. So it will extend out a plus b units still, and it will flatten at a minus b units on the opposite side. So this is negative cosine, so it should go out all the way to 4 here, 3 plus 1. It should come around, but it should sort of flatten out, sort of like a flat tire there. That should be more of a smooth curve here. But it should sort of flatten out like a flat tire on the side there over at 2 units, because 3 minus 1 is 2. And if we put that in here, r equals 3 minus cosine theta, that's, I may have accentuated that flatness a little bit more than it shows here, but it just sort of flattens out. It's not a circle, it's just kind of like a squished down circle. And the larger the ratio, right, the more it begins to resemble a circle. So if I get down to a 2, it looks much more flat. But the larger value I put in there, the larger the ratio is, the less flat it becomes. And the same thing applies. If I change this to a plus, it's just going to flip it around. If I make it a sine, it's going to, that's not sine, it's going to flip up. And if I make it a minus sign, it will flip down. All the same symmetry that I talked about earlier will still apply. Good or no?
Good.
Great.
Ah, wonderful. That's spectacular. So that's basically what there is to know about lemniscus. I'm not going to assign you anything to like practice graphing them because I think it's pretty straightforward. Just learn the ratios and learn how far in and out it goes. And here is just sort of the basics of it, that if a over b is less than 1, it doesn't say greater than 0 there, but we always talk about a and b being positive numbers, so a over b will never be less than 1. And you get the inner loop. It's heart-shaped, it's cardioid. Right? You get this dimple, this little sort of little dimple that's not a pole, and then we get this flattened side, no dimple, no loop. That's greater than or equal to 2. So if you need a second to write that down, you're welcome to, but my guess is you've all got all of that sort of down already. Everybody good, or do we need to wait there for a second?
I'm good.
One person is good. Perfect. All right. So let's move on and talk about something called rose curves. Rose curves are another wonderful polar graph. They look like flowers. That's why they're called rose curves. So we've got r equals 4 sine of 2 theta. anytime you have, we'll just call this R equals A cosine n theta. So some constant and then some coefficient on the theta that is greater than 1, some real number, integer constant that's greater than 1. It's a rose curve, and it's going to have these little petals to it. And we'll see what it looks like in just a second. Couple of things that we will note is that the A value, A equals 4 in this case, and then each petal that we have on this, each petal will extend out 4 units from the pole. Okay? So we're going to have petals that stick out 4 units. If n is even, then we have 2n petals. If n is odd, then we will have n petals. So in this case, we have an n value that is even, so we should have double that number of petals. So this curve, this rose curve, should have 4 petals that extend out from the pole 4 units each. Everybody good with that so far? I know we haven't graphed it. I know we don't know what it looks like yet, but we're going to do that in a second. So all of the petals are identical. They're all completely symmetric to each other. They're all identical, and they're all evenly spaced around the polar grid. So if I have 4 petals, each one of them should be spaced out by pi/2 radians, right? Depending on where the first one is, the next one will be pi/2 radians from that, the next one will be pi/2 radians, and the next one will be another pi/2 radians for this particular one. If I only had 3 petals, then they should each be spaced out 2 pi/3 radians for each one. Make sense? Good or no? Okay, so let's plot a few points for this one. If I plug in theta equals 0, what do I get? For R. Y'all still alive out there? If I plug in 0 for theta, what's the sign of 0?
0.
0. So what's R going to be?
0.
0. Okay. Let's plug in pi/12. If theta is pi/12, I'm looking for the sign of pi/6, which is what's the sign of pi/6?
1/2.
1/2 times the 4 gives us 2. So I should be 2 units out at pi/12. If I plug in pi/6, that's going to be 2 times pi/6, which is pi/3. The sign of pi/3 is √3/2 times 4 is 2√3. That's going to be a little bit shy of 4 units. And what about at pi/4? If I plug in pi/4 and double that, that's pi/2. Sign of pi/2 is 1 times 4 is 4. So we now know that we've done half of this petal because we've gone from the pole all the way out to 4 units, which we knew is the furthest out it would extend. The petals are symmetric, so I can not worry about trying to plot these other points and just know that as I go, it should come around very nicely like this. And that's going to be 1 petal of this curve. Now we know that they're all evenly spaced out. So the furthest out point of this first petal is at pi/4. So where should the furthest out point of the next petal be? Should
3
be
pi/4.
3 pi/4. So at 3 pi/4, we're going to be out to 4. The petals should be symmetric and identical to each other. So we should have another petal It looks like that. And then from 3 pi over 4, we should have one at 5 pi over 4. And out at 7 pi over 4. And that's what this rose curve should look like. My drawing isn't actually that atrocious, but we'll put it up on Desmos anyway. There it is, R equals 4 sine 2 theta. Good or no?
Groovy.
Good. Wonderful. All right. What would happen, just real quick, if I change the 4 sine 2 theta to sine 4 theta?
There'd be 8
8
petals.
petals.
There should be 8 petals, so let's do that. Oh, look at that. Oh, I made it 8 theta. Let's do that. 4 theta, there's 8 petals, right? Yeah. And we would just have to figure out where the first one went out its full 4 units. And then we could evenly space them all out around there and be good. Same if I made it 6 theta, right? Then there's 12 petals. Or if I made it 10 theta, there ought to be 20 petals. I just need to figure out where one of them is. They're all symmetric and identical to each other, so just space them out evenly across the 2 pi, and you've got your lovely little, oh, that's an odd number. That's why it looks like that. We've got our nice little flowers that we can draw. Everybody good?
Mm-hmm.
Wonderful. Excellent. All right. So here are all the rules for it. I know we just talked about this, right? But if we've got sine of 2 theta, we're going to have 4 petals. If we've got cosine of 3 theta, we're just going to have 3 petals. Even numbers doubles the petal, odd number gives you the same number of petals. The A value is how far out you extend at its maximum. And all we have to do is figure out where the first petal starts. Anybody want me to hang out on this page for a second so you can write stuff down, or are we good to keep going? We're good. We're good, all right. So 3 cosine 3 theta. We're going to talk about a cosine one here. First off, how far out should each of the petals extend?
3 units.
3 units. And how many petals should there be?
3.
Should be 3 petals. So how do we figure out where the first one extends out to its max? Well, it's cosine. And when is cosine at its maximum? When the angle 3 theta is equal to what?
3
That's right.
theta equals 0. Yeah.
Yeah, cosine of 0 is 1, right? That's the maximum for cosine. So
Yeah.
that this first petal should be at its max when theta is 0. So 1, 2, 3 units out. If I'm spacing these out evenly, 3 petals across 2 pi radians, that means the next one should be at 2 pi over 3. And then the last one should be at 4 pi over 3. Now, if we want to see just how wide these petals might be, it's sometimes nice to plug in a value or two. If I plug in pi over 12, that's 3 pi over 12 or pi over 4, which gives me 3 times root 2 over 2, which, I don't know, what's 3 times root 2 over 2 come out to be approximately?
$2.12.
2.12 sounds great. So 2.12, 2.12, 2.12, 2.12, lots of 2.12s. Okay. And then what about if I were to plug in pi over 6? 3 times pi over 6 is pi over 2, and what's the cosine of pi over 2?
0.
0. So I'm already right back to the origin, or to the pole. So we should just end up with this very nice looking rose curve right there. Good?
Yes.
Okay. And just for fun, because my drawings are terrible, there it is, 3 cosine 3 theta. We'll note that anytime we have a rose curve with cosine, the value is always going to be 0 for where that first petal starts. So for cosine, it's always going to extend out along the polar axis. For sine, we'll have to figure it out for sine. So we'll talk about that in just a second. So what should this one look like? How many petals should this have?
8.
8.
8 petals. They should all extend out how many units?
5.
5 units, and it's cosine, so where should the first one start?
0.
At 0.
0. And if I have 8 of them spaced out evenly on 2 pi, that'd be every pi over 4 radians, right? Plug in maybe the value of pi over 12 at least. What's the value of pi over 12? That's the cosine of pi over 3, which is a half, and 5 times a half is 2.5. So each of these should be at 2.5. And we're going to see how horribly I do this. That wasn't half bad.
It's like maybe 55% bad.
Wow, thanks. That's really unkind of you. I'm feeling very sad now. No, that's not true. There it is, 5 cosine 4 theta. Desmos makes it look a lot prettier than mine does. Good or no? All right. Let me see here. I hope I have one more. No, I don't have one more. All right. Let's just talk about real quickly. What if the thing was r equals, how about, what do we think? How about r equals 2 sine 4 theta? We need to figure out where this hits its max. So where does this hit its maximum? When sine is equal to the angle that you're taking the sine of. It doesn't even look like a theta at all. When that angle is at what?
Pi over 2.
Pi over 2. So for this one, we would know, and this isn't normally a value that's nicely on a chart, but this one ought to have 8 petals, and the first one should be at its max at pi over 8. If I had one, and then they'd just be evenly spaced out around. If I had r equals 3 cosine 3 theta, no, I don't want cosine, I wanted sine. Cosine is too easy. 3 sine 3 theta, we would just say, well, 3 theta needs to equal pi over 2, as that's when sine is at its max. And so theta would be pi over 6, and that's where the first petal would be at its max. Everybody good with that?
Mm-hmm.
All right, cool. All right, we're going to move on to, we got one more official type of polar graph that we need to be familiar with. This one is one of the few that does not start out as r equals, but it starts out as r squared equals. So r squared equals 4 sine 2 theta. Anything in this form, r squared equals a sine 2 theta, or in fact, I think later on I have this written as a squared. Sine 2 theta or a squared cosine 2 theta. This is called a lemniscus. It's called a lemniscus. And a lemniscus is just a figure 8. So first off, we want to figure out the maximum that this goes out. So it should go out at its maximum when 2 theta is equal to pi over 2, right? Because it's a sine function. So that would tell us that theta is equal to pi over 4. And since all lemniscuts have a 2 theta there, any lemniscus with sine will always be out at its max at pi over 4. So how many units out will this go when theta is pi over 4? Well, it should go out. What's the r value? If r squared equals 4 times 1, what does r equal?
2.
It equals 2. It also equals -2, right? R squared equals 4 gives us r equals positive or -2. So at pi over 4, I should have a value at 2, and I should have a value at -2. What if I plugged in pi over 12? Or sorry, pi over 6. Let's plug in pi over 6. 2 times pi over 6 is what? Two times pi over 6 is pi over 3, right? What's the sine of pi over 3? Still root 3 over 2, right? So this ought to be 2 root 3. So what is r? R is the square root of 2 root 3 plus or minus. What's the square root of 2 root 3? About.
$1.86.
Wonderful. So at pi over 6, we're going to be there. Plus, we're going to do the same thing coming out this other direction. And a lemniscus will always be symmetric. So at pi over 3, it's going to be the same. And then let's do one more. Let's do pi over 12. So if we do pi over 12, we got r squared equals 4 sine pi over 6, which tells me that r is plus or minus root 2, right? Because sine pi over 6 is a half, and half of 4 is 2. So plus or minus root 2, that's about 1.4. And still symmetric. And you end up with this nice little figure 8, sort of tilted on its side. The reason that nothing ends up showing up in quadrants 2 and 4 is if we were to plug in, let's say we plugged in 3 pi over 4. Well, when we double 3 pi over 4, that's going to give us 3 pi over 2, right? And what's the sine of 3 pi over 2?
-1.
-1. So we'd end up with r squared equals -4. And clearly that doesn't have any real solutions. And so there's never going to be anything that pops up in quadrants 2 or 4 for this. It's only going to work in quadrants 1 and 3. Good or no?
Good.
Okay. What if I throw a cosine in front of it instead of a sine? R squared equals 4 cosine 2 theta. What do you think is going to happen?
Maybe quadrants 2 and 4 instead of 1 and 3.
maybe quadrants 2 and 4 instead of 1 of 3. That's a reasonable guess, even though it's wrong. Where does cosine always hit its max?
0.
At 0. So it's going to have its furthest out point at the square root of this value at 0. And it's going to go the same distance out at pi, or the opposite value at 0, -2 and 2 at 0. And so this one's actually going to just lie perfectly nice along, I'm not going to plot all the points, but it's going to lie perfectly nice along the polar axis. So it actually has some pieces in each quadrant that, because of the nature of cosine being at its max at 0, it lies across them. Good or no? All right, so here are the basic rules of Lemniscus. It talks about the symmetry there, and that the sine ones will always be in the first and third quadrants, and the cosine will always lie across that polar axis, and they're always symmetric like that. Any questions or issues with any of this polar stuff so far? All right. Last one we're going to graph here is r equals theta. So if we want to graph r equals theta, what's that going to end up looking like?
A spiral?
It is going to look like a spiral. So when theta is 0, r is 0. But when theta is, let's say, pi over 12, so is r, right? Which means pi over 12, that's about a quarter. So I'm just going to be a tiny bit out here. And at pi over, I don't know, let's go up to pi over 3, we're going to be already almost out to just over 1, right? And maybe if I put in the pi over 6, maybe that'd be good. It would be a half-ish. And then at pi over 2, we'd be at about 1.5. And then at pi, we'd be just over 3. And let's say at 3 pi over 2, we're going to be awfully close to 5. So we're just sort of spiraling out. And this is called the Spiral of Archimedes, for any of you that have interest in these sorts of things. Pretty cool, huh? We get a nice little spiral. And just for fun, let's throw this up here on Desmos also. There's r equals theta. What do you think would happen if I made that 2 theta or 3 theta? Is it going to loosen up the spiral or tighten up the spiral?
Loosen up.
Should loosen up that spiral, right? It shouldn't be as clearly a really cool spiral. But if I were to make it like a half of theta, right, it's going to make it a tighter spiral, or a quarter of theta. It's going to give us this really cool looking spiral, the Spiral of Archimedes. Good? Any issues, any problems, any questions, concerns, complaints?
Can you, oh wait, can you like put it back and then like keep zooming in?
Well, yeah, I guess. What would you like me to put in? A quarter theta?
Yeah, sure.
Okay. I've zoomed in. It
gets less impressive the closer
yes,
you
it
get.
gets less cool.
It is cool
Yeah,
for the
because
first
remember-
quarter of a second.
Yeah, it looks cool for a little bit, but then it's only got us to 12 pi here. But yeah.
Wait, what if you do like 0.02?
mean, it's still eventually gonna, wow, it's like, thinks it's having trouble graphing it because it's just so difficult. It makes it look linear. But yeah, I mean, it's still eventually, the further you zoom in, it's just gonna look like a regular old spiral again. It's never gonna be like super tightly wound around here. I mean it is, but like, put another 0 in there, sure it is, but like if I zoom in just a little bit more, it's no longer. If I put another 0 in, well, sure looks like it, but if I zoom in again, well, then it's not anymore, right? So you'd have to put a lot of zeros here for us to be able to zoom in for just even a little bit. And then already it's just looking like not that exciting again. Good? Not good? Anybody else have anything else they want me to like play with here with the Desmos? Just for fun. Yeah, that's right, Derek. No acid trip. Very sad. Yeah, and you can get all kinds of like weird looking functions in here. If you do other polar stuff, let's see. I don't even know. Like, let's put in. Nah, that's no fun. Sine theta, tangent theta. Oops. Why is this thing? There's nothing there. Yeah, that's not very interesting either. Well, yeah. Sometimes you can get some cool looking stuff. Let's throw in like, yeah, there we go. This is what we need to do. That's fun. Get some like cool looking little design looking things here. If you, especially when you play with the values of the.
Wait, zoom in on that.
Okay. Yeah, it's pretty cool. Look at that. Oh, and now, oh, no, there's still more to it. No, not really. Was that good for you, Derek? Did you enjoy that acid trip there?
Most definitely.
Oh, good, yeah. And these little pieces that keep popping up inside of here. Oh, we lost Denise. Denise is back. These little pieces that keep popping up inside of there, because of the tangent part of that function. But yeah, it's pretty cool. You get some cool stuff with these polar graphs. So anyway, that's that. Yeah, it did kind of look like a spider web or a spider, didn't it? So that's really all you guys need to know about polar functions. Anybody have any questions on the polar coordinates, polar functions, anything we've done with them?
For the rose curves, if we change any of the values to negative, will it affect it in any way?
We won't do that, but let's see. 3 cosine of -2 theta. It just looks, oh, that's 3 cosine. What that's supposed to be. That's the right graph, but I don't know. Yeah, it's going to look exactly the same. The sine ones will, for cosines, will look the same. The sine ones, let's see. If I have like an odd value in there, it's going to sort of flip it around a little bit. So like -3 to 3, it just sort of flips it. I'm not going to give you any with negatives in there though, so I wouldn't be too worried about that. That's all it's going to do. So ones that are already like perfectly symmetric, they're technically, like this one is technically, when I change it from -2 to 2, it's technically flipping. You just can't see that it's flipping across the polar axis. Whereas with the 3, you can obviously see that it's flipping across the polar axis. Right? But yeah, that's all it does. It just flips it across that axis. Any other questions?
If I may ask, what do we do with these? Like, what do we use them for? What do we do with them?
Well,
later?
For right now, we're not going to do anything with them other than understand what they look like. They are not super commonly used unless we're talking about like how particles move in a plane. So we're going to do some of that with like how a particle might move in this two-dimensional space, rather than last year how we talked about how particles move in a, we did particles moving in a line along the x-axis or along the y-axis. We're going to do the same thing here, except we're going to have particles that are moving according to this equation, and we're going to have to deal with that. And there's not a lot of real practical applications that are not in like higher up science stuff, like with the motion of like the atoms in a molecule and that kind of junk. That some of that stuff can be modeled using polar equations. The basic application of this would be architectural things. So like if you're trying to, think about any Catholic church that you've ever seen, perhaps, like they've got, their rows, windows, and these intricate designs and all of that. And then, well, if you're trying to be the person that's constructing that, and you need to know exactly how much, iron to be able to bend to turn it into something that you can possibly make these nice stained glass windows out of, well, you might need to know exactly how long this arc might be. And so that's something that we will learn. Or you might need to know exactly how much glass you need to purchase to fill up all red stained glass in this piece of it, and blue in other pieces, and stuff like that. So we're going to do things like that where we look for the area within these curves also. So that's kind of where we're going to do with it, is just the basic applications of it, but there are some higher applications of it in higher science and higher math classes also. Does that answer your
Okay,
question?
thank you. Yeah.
And we're also going to do some of the basic stuff, like with, we talk about derivatives. Well, we're going to want to be able to figure out what's the slope of the tangent line to this at any point, because those sorts of things, are applied in both the basic applications of these and the higher applications as well. Any other questions?
I had one. So when you're picking theta values for the sine ones,
Yeah.
how do you usually pick your theta values for like the sides of the petals? So I know how you would figure it out for like the one where it extends fully, but for the other ones on like the side of like the petal, you usually used pi over 12 and pi over 6. Is there any way you'd like specifically pick those?
Yeah, I mean, it doesn't really matter. If suppose we have 5 petals, which is like an annoying one because the numbers don't line up real nicely. Well, except that this one ends up nicely at pi over 2. But since we know that they're spaced out by like 5s, I might take 1/5 of the distance between them. So if it's, if the distance between them is 2 pi over 5, I might take a value that's like 2 pi over 25 over from here, so that I can also have that value that's 2 pi over 25 over the other direction, is what I would use. But I'm not going to give you, I'm really not going to have you graphing these so much that you need to know the exact little coordinates of each thing. I just want you to know the basic general idea of it. Like, hey, this one is sine 5 theta, so it's got 5 petals, and the first one goes out there at pi over 10. Right, that's good enough for me, because all we're going to do is say, oh, find the tangent line at this theta value, or find the area inside one of these petals, or find out how far a particle travels if it starts at the pole and goes and traces one loop of the rose curve, that kind of stuff. So you're not going to really need the exact points, but I would just do it by taking a fraction on either side. It's like 1/5 this way and 1/5 this way of what the range is. Does that make sense? Does that answer your
Yeah, it
question?
does. Thank you.
Any other questions?